¿Vale? Ujú. Venga, pues buenos días a todos y a todas. Pues seguimos, ya lo sabéis, con el ciclo de seminarios de aquí del Instituto de Estructura de la Materia de este año 2025. Y hombre, un poco recién aterrizados, a que sí, de Semana Santa. Pero vamos a dar la bienvenida a Francesca Vidotto, que acaba de sacar la plaza aquí en el Instituto de Estructura de la Materia, en el Departamento de Química y Física Teórica, y claro, nos va a hablar de su trabajo de gravedad cuántica, y para ello pues nos la va a presentar Guillermo, y creo que va a ser en inglés, ¿o no? Welcome all of you, and Guillermo is going to introduce Francesca.
La introducción la voy a hacer en español, ya se lo he dicho a Francesca, la charla la dará ella en inglés. Bueno, esencialmente Vicente ya ha comentado lo más importante. Francesca obtuvo plaza de investigadora científica y se incorpora en julio al instituto. En el grupo de gravitación y cosmología. Ella es bastante famosa y conocida en lo que llamamos Loop Quantum Gravity, en gravedad cuántica de lazos. Entre las características que tiene, aparte no voy a repetir su currículum, ella ahora está en la Universidad de Western Ontario. Es muy probable que venga con un proyecto bastante importante, la Templeton Foundation. Y sí que quería comentar varias cosas. Es una persona que tiene una capacidad increíble de interactuar y buscar puentes entre muchos temas. Y además es una persona con una capacidad de divulgación bastante llamativa. Ha hecho cuestiones desde teatro científico, charlas TED, prácticamente lo que podáis imaginar en estos campos. Entonces yo creo que es un buen fichaje para el instituto. Esperemos que todos salgamos beneficiados. Para cuestiones de divulgación toma nota, Vicente. Y nada, que es un placer tenerla aquí. Y le cedo la palabra a Francesca, whenever you want.
I think sí. Muchas gracias, Guillermo. Soy como I'm moved. Creo que necesito hablar en castellano, en español, porque, bueno, estoy practicando el idioma, pero no lo tengo bastante bueno por hacer una charla entera y también no lo tengo bastante bueno por explicar cómo que siento, how much grateful I am for this introduction, for Guillermo, who helped me to come back to Europe from Canada. And how much I look forward to meet all of you and to get to know you better. So, yeah, I mean, maybe Guillermo was a bit exaggerating, but something is true in what he said, that so my work that is in loop quantum gravity, in cosmology, I tried to touch on many different things. So the presentation of today is really to give you an idea of how different things that may seem also very diverse may connect, and maybe also the place where we can find collaborations together. So notoriously, quantum gravity and loop quantum gravity is something that we have tried to search in the sky. And the talk of today is focused and starts at least from how to bring quantum gravity down to Earth. So this is where I want to start from. This is a bit of a list of topics that I hope to touch today. 2 and 3 and 4 are the core of what I want to tell you. And I will just go briefly, if I have time, into just give you a glimpse of some ideas, 5 and 6, about what I'm doing and what I would like to do next year, connected with what I will tell you. And yeah, so that first of all, I talk about quantum gravity, but my the framework in which I work is loop quantum gravity. That is a sufficiently well-established theory so that we can do computations, we can make predictions. So usually the joke I make is that if your theory can stay in a t-shirt, you know that you're good, and it means that the theory is sufficiently well developed that you can work with it and give computations and give predictions, especially. So, and of course, especially here, we have been people have been working a lot on the application to cosmology. This is also actually my main research. how a loop quantum gravity cured the initial singularity, and so all the possible signature that may come from a universe that doesn't have a Big Bang anymore. It may have a bounce. So you don't have anymore the classical singularity that comes from general relativity, where you have an infinite curvature, infinite energy density. Instead, quantum gravity provides a way to avoid the singularity. It's cured by the quantumness in the same way in which you don't have the catastrophe of electron falling into the nucleus of an atom. In the same way, the quantization cures the cosmological singularities. So there is I mention this because this is something you may have heard, since here there has been, here the Institute has been one of the main centers for the research on this. But again, I wanted to go somewhere else to look for reality check, because of course we do the theory. I show you the T-shirt. There is on one hand the consistency of the theory in itself, but also we need to connect with experiments. We usually connect with experiments looking in the sky, and we had already a lot of answers for how a theory of quantum gravity should be. So sometimes people say that quantum gravity is too far from our scale to make quantum gravity experiments. So of course we don't have a direct access to the Planck scale. This is true. But on the other hand, we do have a lot of quantum gravity measurements. I want to say we already had, and these are the constraints that guide the way in which we construct our theories. So these are a partial list of ideas of possible quantum gravity signature. Some of these things have given negative answers, but even negative answers imply that we have constraints. So we are on a stronger ground on the theory we work with. And the next step is instead of looking in the sky for these signatures, can we look for a signature here on Earth, on our labs? So as I said before, of course, the strategy will not be the one of building larger and larger accelerators. So then we can prove an energy scale that is higher and higher. Quantum gravity phenomenology is about being creative, and I would like to tell you a story that is prototypical of how physics works, with just a sparkling creativity that open up a completely new field of research. So I'm going to talk about tabletop experiments for the search of quantum gravity. So these are experiments that, again, they may be performed maybe in your own lab. And I want first to put a caveat, because, of course, I'm talking about history that is, I want to tell you about history that is relatively recent. It's 5-6 years old, let's say. But people have been talking about measuring quantum gravity in the lab for many years, except that from the point of view of a theorist, from the point of view of somebody working in quantum gravity, those experiments that were proposed were not really hinting to quantum effects, and they were somehow set to fail. For instance, so I make here 2 points that when we want to measure quantum effects, so the core of the quantum theory is about measuring, on one hand, the discreteness, and on the other hand, measuring superpositions. So if you take discreteness as the main feature of quantum gravity, you want try to measure it. Again, all the experiments that have been set so far were rather measuring averages, and when you measure averages, you don't expect to see the fundamental quantum discreteness anymore. So that's why I was saying these were somehow set to fail. So, but what about actually going for the superposition directly? And again, this is not something completely new. Even Feynman, in the famous conference of 1957, it was the first conference, I sometimes consider the first conference in general relativity. So even back then, Feynman notoriously said that if you have two objects that are in a quantum superposition, if these objects have a mass, you should also expect that there should be a superposition of geometries, because each of these mass has its own its own gravitational field, its own gravitational potential, and hence two different geometries that can be in a superposition. So, of course, so this is something old. So what's the novelty here? So the novelty comes with a proposal, you see, from 2017 by Sugato Bose and collaborators. So it's a new setting that I'm going to tell you about. So you start with two particles. So here I have, you have to look at this as, so here I have a time that passes. Here I have the distance. I have the distance between the two particles, this purple and green one. They have the same mass for simplicity. So they are basically the same particle. And what I do is that I split them. So I split the first one in two particles, saying spin up, spin down. I split the other ones. And as you can see here, I basically describing the states, the total state, as given by the sum of four possible states, so four possibilities. You may think that I have the particle going this way, and this other particle going this other way, so they are like left-left, then the opposite, right-right, and then the interesting part comes when you have either, well, left and right, so the two opposite direction, let's say, and here there is what we are interested in. So there is one possible path in which you have, here we indicated as right-left, is one path in which the two particles come close enough so that they can feel each other gravitational field, namely they can interact gravitationally. So if there is an interaction, if one path has an interaction, so of course let me say that the particles always feel the gravitational interactions of everything, right? So in principle you have an interaction, gravitational interactions between this path and this other path, but the idea is that this interaction is extremely small and is not enough to create this entangling effect. So one of the difficulty of these experiments is exactly to have one path with this peculiar strong interaction and the other path such that the gravitational interaction is not enough. That means that you have to separate the two paths. So when you create the two particles in a superposition, you want to separate them enough. So then you can have a distinguishable effect between one path and the other. So the central point here is the fact that in quantum information there is a theorem that tells you that if two particles that start being unentangled, they end up being entangled, and this happened through the fact that they have interacted. This is possible only if the mediator of this interaction is a quantum mediator. So if the field that carries this interaction has quantum properties. So as I said, the important thing is in this experiment, so you want to perform the experiment, and you need to be careful in setting up the experiment so that the distance here between the two particles is sufficiently small. So you have to control the experiment to have this short distance, but at the same time also to have a very large distance between these two branches. And there is a very simple way to understand geometrically what's going on, what is causing this entanglement that should be visible in the resulting particle once they recombine after a path. So concretely, what you see in the end, if there is entanglement, is the presence of an extra phase in the final state. And this extra phase comes from, of course, the gravitational interaction. And you can see that this is a very peculiar regime for quantum gravity, because we are just considering a Newtonian potential. But again, we have geometries, space-time in a superposition, and the difference between these geometries is accounted by the fact that different geometries have different so if you can say, we can say time flows differently in the two paths. So, the particles that fills different geometries, they have their internal clock that ticks differently. So we have, in one case, so depending on whether the particle follows one path or the other, we have time dilatation. And this is this time dilatation that is what brings the final extra phase. So you can really just make the computation of this extra phase that is given by this number. And so you can see that in the end, the extra phase depends on the ratio between the mass of your particles and the Planck mass. And then it depends on the geometry of your apparatus. Namely, it depends on the distance between the two particles that are interacting, and this quantity d that I was showing you before. So it depends on d. And it depends on the time interval in which the particles are interacting. So basically, so this depends, as I said, by how massive are the particles you are able to put in a superposition. And this depends on the geometry of your apparatus, the distance, and how long you can keep the particles into a superposition. So this is basically what gives us the experimental boundaries of these proposed experiments. So you need to have particles as heavy as possible in a superposition. And I mean, this is from some years ago, but already in 2018, we were talking about micrograms. So the other aspect is to have, yes, we say control of this over this distance, but also screening this effect from the interactions that could appear in the other branches. So this means that, as I told you, that we need to put in superposition particles that takes larger and larger path. So this, so a few years ago, we were at half a meter scale for this. And then the question is for how long you can keep the particles in a superposition. What we need for these experiments to give significant effects, the measurable effects, is to keep the particles basically for around 1 second in a superposition. And well, I'm not myself the expert of this. We collaborate with the lab of Markus Aspelmayer. This is a picture took in Vienna last week. I was there for a conference. This is the kind of apparatus that they are using. It's really physics down to earth. It's really tabletop experiments. So of course, for the moment, we don't have the actual experiment yet. So what people are doing is just to push the boundaries I was telling you before, trying to push the boundaries for keeping the superposition longer and longer, larger distance, heavier and heavier particles, and so on. And as Guglielmo was mentioning before, in the past 6 years, we have been developing a collaboration between people in quantum gravity, and specifically loop quantum gravity, and people in quantum information, and people in philosophy of physics, because we need the interplay of all of these different communities to try to address how to understand this kind of experiments. And but the collaboration goes beyond just the experiments. So the next thing I want to tell you about is how we go from the tabletop experiments back to the sky. So this is what I plan to do and the rest of the talk. So yeah, so from the lab, let's go back to the sky and let's talk about dark matter. Why? Because the kind of setting of these tabletop experiments to measure quantum gravity are exactly the kind of setting that can be used to detect particles that interact only gravitationally with your detectors. So dark matter, by definition, is such a kind of matter. A matter that doesn't have any electromagnetic or any other nuclear forces interaction. You need to have something, you need to have an apparatus that is sensitive only to the presence of a mass that is passing through it. So think again to the setting that I told you before. Actually, you can have something even simpler, like you can have two particles that are sitting there, and then you may have, say, one massive particle that passes nearby your device, your detector, that again is just made by these two particles, and you may have a situation in which only one of the two particles, sorry, I was forgetting about saying something. Of course, so the two particles here are one particle put in a superposition, but only one branch, only one one of the two superposed particles feel the presence of a dark matter particle passing nearby. So when they are recomposed, you can see again this extra phase provoked by the interaction with this mass. So this seems too difficult to be done in a certain sense. So if you have just one particle in a superposition, what are the chances that you have a dark matter particle getting close enough to create the situation to have a detection? But this is not so crazy because people have been developing this kind of detectors for many, many years. Well, they were thinking about different possible masses for dark matter, depending on what's your favorite dark matter candidate. But basically, the setting was this, except that you replicate your single detectors into many, many detectors. Specifically, what you can use are Josephson junction that are basically like O-ring, but with a hole, and then you put you have basically electrons that gets into a superposition. They can be on one side or the other of the hole in your O-ring. And in case you have the interaction with massive particles, so this the Josephson junction is such that it creates a current that can be detected. And as I said, of course, you cannot do this with a single object, a single Josephson junction. But the good thing of these objects is that they are cheap with respect of other projects for detecting dark matter, certainly much cheaper than, again, colliders and so on. So you can make large detectors by multiplying your single detectors. And eventually, you can have, you can make it so large, and you can have possibly a different location around the Earth, so that you have a chance to see a dark matter particle passing through it. So let me start to be a bit more specific, because I have a favorite dark matter particle that I want to talk about now. So the kind of particle I have in mind is a particle that has a Planck mass. So I'm interested in quantum gravity, so let's go towards the Planck scale. Let's go to a Planck mass. So except that the Planck mass is not so far away. It's like a piece, say, not even a piece of hair. It's like, as we say, like a few micrograms. So again, it's perfectly in the range of detectability of these proposed tabletop experiments. So again, so this is an example from given from a review of possible experiments that use similar technologies. Here, people are not really so they use a different language than what I used to present you this tabletop experiments in which you have gravity-mediated entanglement. Here, it's phrased just in terms of having the most sensitive experiments from dark matter particles, but basically the idea is the same. And as you can see here, you can try to prove in this way different candidates for dark matter. I'm interested in It's something in the between. You see here there are primordial black holes. You see some other. So here you have the Planck mass. So this is basically where you want to be with the WIMPs, with the weakly interactive massive particles. And I wanted to tell you about my favorite candidate for an object that can be detected in this range. Namely, so, okay, just to again, to give you an idea, of course, for dark matter, we have a lot of different candidates. Again, if you are a good natural philosopher, I think you have to pick up your favorite, because being agnostic doesn't help so much. You have to make your bet. And my bet is on this part these days, in which you can find, as I say, the primordial black holes. But primordial black holes that are very small, basically they are the same thing as macho or as WIMP. So here there is a big family of objects, of possible objects, whose characteristic is that they don't need really new physics. And what I mean by this is the fact that you don't need to add dimensions to the universe. You don't need to change the standard model of particles. You don't need to modify gravity, besides just quantizing it. So you have here candidates that are conceptually minimal, and I think now we are urged more and more to explore them. And the reason, if you want my take on this, the reason why people have not explored them more before is simply because they are more difficult to falsify. So you can go for something very exotic, and this is easy to falsify. And you want to, if you instead try to be a bit more conservative and look for these things, the problem is that it needs more patience. But again, maybe I will convince you that we have a good idea for how to make some measurements for them. So in general, I have a big love for primordial black holes because they are part of these categories of candidates for dark matter that don't require new physics. In fact, a lot of the known physics may produce them. So you have a lot here, a list, a long list of possible mechanisms with which black holes may form in the early universe. Usually people focus on just direct collapse of primordial inhomogeneities. But I will arrive in the end at the bottom of this list. So yeah, okay, primordial black holes, the most common story you are given is that at the beginning of the universe, say for instance after inflation, when you have the so-called reheating in the thermal history of the universe. So the universe is just a sea of photons that is mostly homogeneous and isotropic, but of course you can have fluctuations of energy density, and you need just a density contrast of 0.5 in energy density to have a collapse and form a primordial black hole. And yeah, I just wanted to mention briefly, these are the current constraints. Here in this graph you have the mass in grams, or it's better to see this graph comparing the mass with respect to a solar mass. So the solar black holes with the solar mass are here. So you see there is a nice window in small, in the size of small planets. So this is a window in which you can have all the dark matter being primordial black holes. You have also a window here that is for very large black holes, but again the problem is that so these are very difficult to exclude. And then in this graph you see something that is an exclusion here because black holes that are very small, black holes that form at the beginning of the universe, and they have a mass that is less than 10 to the 15 grams, are expected to have evaporated by today. So that's why they are excluded here. So what I want to tell you about is an idea that comes from quantum gravity about what happens at the end of evaporation, so that you don't have to disregard completely this part of the graph, in the sense that, yeah, okay, maybe you don't have a black hole anymore, but maybe you have what remains after the black hole has evaporated, so a remnant. Yes?
So this graph is for H as 100% of the dark matter?
Yeah, of course you can have so what this graph represents is the fraction of black holes so you take like a line here, a vertical line, and this would correspond to have all the black holes of that mass being dark matter. And of course, one thing that we have understood in the past years is the fact that we can have a mass distribution. So black holes, primordial black holes can form with a possibly wide mass distribution. And thank you for this question, because so this allows me also to make a remark. So in the past, people were focusing on dark matter particles coming from modification of the standard model. And one of the features of those models were that, okay, you modify the standard model, then you have a dark matter candidate, but you cannot have another dark matter candidate, because this would mean a different modification of the standard model. So in the past, we were focusing on the fact of having just one type of dark matter, and it was impossible in that context to have a different source of dark matter at the same time. What is nice with primordial black holes is that they are compatible possibly even with other exotic form of dark matter. So they don't have to constitute all the dark matter. Of course, we love them, we want them to succeed in doing their job, but yeah, they are compatible with other dark matters. They are interesting for us nevertheless. And for the sake of what I want to tell you, so you can form primordial black holes with different masses. Some of these masses may be in the range in which the evaporation has already taken place. And then you can have still some remnants, and the presence of these remnants is compatible either to have all the dark matter being remnants, or possibly having, most likely in my opinion, having a mix of these different dark matters. But again, it's a homogeneous in the sense that they all start as black holes, but they are black holes in different phases of their life. So let me tell you about this proposal, black hole remnants. And the novelty comes from, so the novelty from loop quantum gravity comes in two ways. One way is the fact that, as I told you, loop quantum gravity removes the classical singularity of general relativity, and in particular, cures the singularity inside the black hole. So you can ask the question of what's the dynamics of the geometry, how the geometry inside the black hole evolves. And of course, Guglielmo here and his students also have been working on this, writing the equation of the evolution of the interior of the black hole. You can see how this interior is not singular. The evolution is not singular. And most importantly, something that students unfortunately are not told at school when they take General Relativity 101, or whatever you call it in Spain, is the following fact. So when black holes form, so of course, for instance, you have a collapse, could be the collapse of a star, could be the collapse of matter in the early universe, whatever you like. But the point is that what defines the presence of a black hole is that you form an horizon, And inside the horizon, in the moment in which the horizon forms, here I'm talking, well, for those of you who are in general relativity, this is rather a trapping surface, not an horizon, but nevertheless. So you form, you give a shape to your object, and the point is that the internal volume in that moment starts to grow in a way that is much bigger than the corresponding Euclidean volume that you would associate to an object from the outside with that particular area, okay? So like imagine, we have this intuition that a black hole is like a sphere, a black sphere there in the sky. But in fact, the point is that the geometry in the interior is such that in the moment in which you form this object, the interior starts to grow and expand. And the more the black hole is old, the more this space grows and gets larger and larger. So what we are seeing in loop quantum gravity is the fact that this process can continue, and so this volume can grow and grow, and eventually you can have a bounce so that the process is reversed. So this is illustrated there. And, oops, yeah, no, I don't know what happened. Well, okay. I don't know how to make it. Control L? Sorry, I'm a Mac person, unfortunately. I'm ashamed of this, but it's getting even worse, okay. Can somebody help? I can tell you about black holes nevertheless. So the interesting thing now is that keep in mind that you have this very large interior. And imagine now that the black hole is evaporating. So evaporating means that its size, as seen from the outside, is getting smaller and smaller, except that this process is much faster than the time it takes for the evolution, let's say, to bounce and then possibly reabsorbed into the outer fabric of the universe. So the way in which you should picture this process is that you have this large volume, Hawking evaporation, you have the onset of Hawking evaporation, the throat that connects the interior with the exterior shrinks, and you still have this large volume, and you have now a throat, but in loop quantum gravity, we were talking before that signatures of loop quantum gravity are discreteness and superposition. So let me use the discreteness here. It's discreteness, but it's discreteness in geometrical observables in quantum gravity. So gravity is about geometry. What does it mean, geometry? Means like what the good old Greeks told us. So we measure the land, we measure area, volumes, angles, and in particular, we can see that areas. So all these observables are quantized, and namely, they appear to have a discrete spectrum with jumps between eigenvalues. And so there will be a minimal eigenvalues. And this is true in particular for the area. So when we characterize the horizon of a black hole through its area, the evaporation shrink this area, but it cannot shrink below the minimal area, okay? So this is a way in which you can stabilize your object. You have these black holes with large interior and the throat that doesn't shrink to zero, but sits on the minimal eigenvalue. In fact, if you are a quantum mechanics person, there is even something more funny that is happening here, because if you have a system that can be in two different states, Well, you know that the state of minimal energy in which your system would eventually sit is the superposition, is a state that is the superposition of these two states, say up and down, spin up and down, or something like this. So in this case, what we have is an object that has the size of a Planck mass, and it sits in two states that correspond to two different geometries, and we can talk about these geometries as being a black hole metric and a white hole metric, being there together and characterizing the fundamental state of these objects. So the remnants, of course, they are not black, they are not white, they are truly quantum objects in a superposition. And before I hope I am like exciting you about this possibility, but of course, if you go out from this room and you tell your friends, oh, I think remnants are awesome, you may hear people saying that remnants are not possible, because in fact, oops, I think I'm doing something wrong here all the way. Control L, no. Okay, somebody help. Okay, yeah, you don't want to see the names of these bad people who first got in love with remnants and then they discarded them, and they got caught, thank you, Gianluca, in the idea that inside the remnants there were not sufficient microstates to accommodate for the information entangled with the Hawking radiation that is outside. And again, this is a misconception that is based on an act of fate into holography, that is the fate into the fact that you can describe all the physics through the information that stays on the boundary of a system. So I tend not to believe this kind of things. As I show you, if you take a proper course of general relativity, you know that there is this very large volume inside, and you cannot disregard this volume, and the volume of course can accommodate for all this information. So that's why I think this is not a relevant counter-arguments. So let me skip this. I wanted just to say something more regarding remnants, because I say the remnants are not black holes, they are not white holes, they are quantum objects, and they are objects that eventually can let the information leak out, except that this may happen in a time that is extremely long, much longer than the age of the universe. So the minimal estimation for the information to leak out from these objects is in a Planck unit given by m to the fourth, where m is the original mass of the evaporated black hole. So just to give you some numbers, so if you have a solar mass black hole that has evaporated, the evaporation in itself in a Planck unit goes as m cube to the third, and it takes 10 to the 50, 10 elevated to 50 years. Okay, it's much, much more than the age of a universe already. So now if you do m to the fourth, this is an horrendously, it's like eternity basically. So these objects are extremely stable. This information leaks out in a very long time. Of course, if you have a mass that is small enough, maybe this leaking of information out can start to be relevant, especially if you have a lot of these objects and they are all leaking out information in a form of radiation with very low energy photons, extremely long length photons. Well, then maybe you can compute the integrated emission given by all these objects. So this is something we tried to do with my students and collaborators. We are also trying to explore this more in the context of a bouncing cosmology. So, of course, the goal at this point is to make everything consistent and not just. So, I think we got convinced about the viability of this proposal for remnants, but to make this idea viable, you also need to cook up good cosmological models in which the remnants appear naturally as dark matter or as a part of dark matter. And so this is what we have been working on. There is some work in progress. And in particular, let me go back to this slide in which I was saying that primordial black holes cannot just form after the Big Bang or after the Big Bounce through all these different processes. There is also one possibility that is considered in the literature, that is to have primordial black holes formed in a bouncing universe in the collapsing phase. So if you have a pre-Big Bang scenario, in which the current expanding phase comes from a previous collapse of another universe, let's say another eon of the universe, then this is also the place in which you can form, you can form primordial black holes. And so let me skip this because I want to directly to go here. So here you have different ideas by people like Brandenberger and Quentin about how to form primordial black holes in the collapsing phase. And you have ideas by people who have been working for very long on primordial black holes like Bernard Card about how these black holes formed in the previous eon may pass through the throat, let's say, of the bounce. Now, this work implies, of course, a lot of care in having the black hole that forms and the collapse, and then they should not get too close through the bounce, because otherwise they will form just a big, large black hole. So we don't want this. But notice that if in fact you have not black holes from a previous universe, but you have remnants from previous universe, those may pass through the bounce completely undisturbed. There is a bit of misconception from people who don't work with equations of a bouncing universe. That is the fact that in order to reach the bounce scale, you need to go down to the Planck length. But the bounce is not something that happens in length, it's something that happens in energy. And if you take everything that we see in the universe today and you squeeze it in the minimal sites so that you have a Planck energy density, well, okay, you have to squeeze the universe in the size of a proton, but a proton is as far away from the Planck length as there are order of magnitudes between us and the proton. So this means that if you have Planckian particles, they have a lot of space to pass through in a proton size bounce. So that's why one more reason to like remnants. And so I wanted to conclude just telling you that I'm studying this scenario in which we have pre-big bounce remnants that may constitute the source of matter that can make a matter bounce. So the matter bounce is an alternative to inflation that provides the correct almost scale invariant power spectrum without having to add an inflaton field. Of course, the caveat is that in most models, to make this right, you have to add a ekpyrotic field, but the idea is that this ekpyrotic field can, in fact, be the result something comes basically from the loop quantization. So this is just a sketch to show you that there is some work that is going to appear with such an ekpyrotic bouncing universe. This is the bounce that we have, and we have different domination era in which the ekpyrotic fields dominates, in which the matter dominates, so that we can reproduce correctly the almost scale invariant power spectrum that we see in the CMB. And there are many things that I would like to do, like, as I said, having this derivation of the ekpyrotic potential directly from loop quantized matter, study more the interplays between small remnants and large black hole, large primordial black holes, and so on. So this is my last slide. I wanted to conclude flashing you something where I want to go in the next year with all this model. I hope there are some people doing gravitational waves in the audience. Yeah, because this is where I hope to go. So, so let me. So we have these bouncing models, and one of the questions that one needs to address to make the bouncing model viable is to study whether they produce primordial gravitational waves. So a pathology of many models that have been studied is that primordial gravitational waves can be produced even in a quantity that is not compatible with the observations, namely the bounce produce too much gravitational waves. So you want to have a model that is viable with respect to this. And there is something that came out recently in the loop quantum gravity community that may open new scenarios. Namely, it has been shown that you can derive from quantum gravity, from loop quantum gravity, a bound on the gravitational waves luminosity. Namely, the luminosity here is the astronomical analog of the power of emission, the emission power. So for gravitational waves, apparently there is a maximum. And this is something that people have been entertaining with for a very long time, especially in the context of emission of gravitational waves from black hole merging. So, I mean, this is something, this was mentioned even in the Bible, in our gravitational Bible, the Misner-Thorn, a Wheeler book on gravitation. You already found some considerations about a possible bound in the luminosity, like a Planck luminosity bound there. People have been observing this even in the numerics of black hole merging. And now my question is, what are the consequences of this for cosmology? So if we believe this, and to me it seems pretty solid because we have a theoretical derivation now, but again, this was something that was kind of seen already in the numerical calculations, and this seems to be confirmed possibly by the gravitational wave detection. So, if so, what does it mean for cosmology? What does it mean for all our models in which we had an overproduction of gravitational waves? Is this something that bounds the production of primordial gravitational waves and possibly cures some of the models that we have discarded? I don't know, and I leave it to you as an argument to discuss together. But I wanted, so I know this is just an idea, but this is something I wanted to show to you again, because this is what it's interesting me the most. And so just to conclude, I started, so I took quantum gravity experiments from the sky to Earth, back to our labs. It's for people doing quantum information, quantum optics, and so on, or condensed matter. I think there is an opportunity to get together and collaborate there. We may be able to see quantum gravity in the lab. Of course, a caveat is that this experiment does not distinguish between different proposals of quantum gravity, but of course, if we make the measurements, and the measurements is that reach in 5 to 10 years, well, quantum gravity will be on a completely different ground after that. And possibly we may also finally put in the drawer for good some other ideas like not quantizing gravity and so on. So this is very exciting. Again, this is something we may be able to witness in the next few years. There are opportunities to do some interesting work that may give result in the short term. And on the long term, who knows, maybe there is this proposal for remnants as dark matter in connection with the wider ideas on primordial black holes as dark matter. And again, the goal is to make everything consistent, everything with also cosmological models that fits with our observation. And that's a grand project. It's a bit overwhelming, but I hope we can tackle some of these problems together. Thank you so much for your attention.
Wow, so ambitious. Thank you, Francesca, for your talk. Time for questions.
Sorry, missed the first 10 minutes, so I don't know if you talked about it, about dark matter detectors. Is there any proposal from quantum gravity to explain the controversial results of DAMA, the annual modulation that has never been reproduced by any other detector?
Well, the DAMA one is with the...
DAMA Libra. Hmm? Yeah, DAMA Libra, I mean, the latest update.
Yeah, but wasn't it, sorry, remind me, I thought there was a possible periodicity of the signal related to...
the seasons?
Yeah.
Yeah, but it's never been proven, so it's still, I mean, it's a possibility, but unless you construct a detector in the southern hemisphere, it's just a hypothesis. But since you were talking about detectors, I was wondering whether there was some thinking about that. Since actually other detectors excluded the explanation of that signal through dark matter, through some models.
And do you remember what was the mass range in which they were?
Between 1 to 6 keV.
Yeah, but I have problems with keV. So in grams, what would it be?
I have problems with grams. So
okay. Yeah, no. In a sense, I think these ideas are rediscovering work that has been done by certain communities. So what I was mentioning in particular is, if I can go. So the kind of experiments I had in mind were more these ones, and they are mechanical. They are part of a large category of mechanical detectors. So I don't know if that what was the technology that Dama was using exactly. So yeah, I'm not sure. I'm able to answer your question. What's the relation between this kind of detectors and the one used by Dama, and hence whether there is a relation or not? I should check it. Thank you, Gianluca.
It's 10 to the minus 30 grams.
Okay, so that would be even smaller than the Planck mass. Again, yeah. So again, so here we are focusing more. So one of the big difference with respect to all the experiments is that they were focusing on masses that were produced by ideas from modification of the standard model. So particle physics, again, we are talking about subatomic particles with those kind of masses. And here we are at the scale of micrograms. So completely different scales. Again, the idea is similar, technology sometimes is similar, but we are in a completely different range of masses. Yeah.
Okay.
Thank you very much for this nice talk. I'm interested in these experiments by quantum optics by Markus Aspelmeier and company. So you have I mean, this is very concrete already, I guess. Yes. So could you tell about the atoms or the molecules that you're using? Because you're splitting them up into spin up and spin down. I don't know if this is the quantum number you're referring to. But then you also have magnetic interactions and so on. You have to eliminate all these. So what is the physical system you're really having in mind? I mean, they have this already kind of.
Yeah, they have it already. Of course, you have to use neutral particles, neutral atoms. So, of course, when you start to talk about micrograms, so for instance, in the experiments that I was mentioning before, we are talking about large molecules to reach the micrograms weight. And yeah, so I have, so we had an entire conference last week about this, but I haven't been, we haven't, maybe we are too many theoreticians and philosophers, so we hadn't asked the question of.
I mean, you have a magnetic interaction. I mean, how do you? I mean, this must be stronger than gravitational forces.
Yeah, it's double. There are two sides of this. First, you need to be fully screened by any electromagnetic or other nuclear interactions between the two interacting particles, but also you need to screen the whole system from any other interaction. Now, of course, the electromagnetic one is the first one you have to take care of. So yeah, I don't know the details of how concretely they do it.
And the molecule?
Yeah, and the molecule. But I would be happy.
What molecule do you use?
I don't know, but I would be happy to facilitate the answer of this question. And there is of course all the people of the group of Markus Aspelmeier that are performing these experiments. And as I said, we have to keep an eye open because there is also this other community of people that is basically reaching the relevant experimental precision to see exactly the same thing. So again, sometimes you see in the literature things that goes under different names, but it's now the moment to pull the strings and bring them together to see that they are all doing the same things, and maybe we can push everything towards the actual realization of the experiment. And the only thing I can say more is that on one hand, so I think in Vienna, they are more finalizing each piece of the puzzle rather than constructing the whole experiment. And there are different proposals about how to make the experiment in itself. For instance, so the original proposal came from the group in London of Sugato Bose, but now there is a young researcher called Richard Howell that has also been working on making different, different geometries for the same kind of experiment. So again, there is a lot of work, different experimental ideas, but I think that the convergence may come in the next few years. I'm sorry if I cannot be more precise than this on that.
Any more questions? Yeah. Tiberio, please.
Thank you very much for the talk. In the same line, I wonder how can you isolate the gravitational field of the Earth, yeah? Oh. Because both particles are filling the gravitational field, right? That's and it is going to be much bigger according to the mass of the Earth, yeah?
No.
I wonder.
No, because so what you are interested, maybe Guillermo can help me with this, because it's really the local interaction, and it's really about, so what we are interested in is the difference between the two paths. So the difference, yes. Yeah, so the gravitational field on the Earth on these scales is homogeneous. It's doesn't change. So I mean, if you, yeah, I mean, of course you have to be careful not to do up and down with your experiments, because otherwise you pick up a time delay due to the difference in altitude, and we know that there is a sensitivity these days to 3 millimeters. You already see the different path, so the time delay and in the recomposition of two splitted path. But yeah, so here is assuming that you have a constant gravitational field, and then you have just a local modification of this gravitational field due to the interaction. Yeah.
Okay, no more question then. Okay, Francesca, thank you very much and welcome.
Thank you so much. Yeah, and I hope you can take time to harvest your questions, so then maybe later there can be some discussion together. Thank you so much for coming today.